Hi, my name is Felix Brandt, and I will present a joint paper with Florian Brandl, which was published in Theoretical Economics. And the title of the paper is Justifying Optimal Play via Consistency. The central question that we study in this paper is why should one play maximin strategies in two-player zero-sum games? We all know that zero-sum games have a much nicer structure than general two-player games. And this is mostly due to von Neumann's minimax theorem, who showed that the best outcome that the row player can guarantee coincides with the best outcome that the column player can guarantee. This theorem has lots of appealing consequences. So for instance, all pairs of maximin strategies happen to be Nash equilibria, and the payoff in all of these equilibria is the same. So for instance, in this example game on the top left here, there are unique maximin strategies for both the row and the column player, denoted here. And consequently, there's also a unique Nash equilibrium, and the payoff in this equilibrium would be 2/3, which is usually called the value of the game. Other consequences of the minimax theorem are that the set of equilibria is actually convex, and Nash equilibria or zero-sum or maximin strategies can be efficiently computed, and this is not the case in general normal form games. So as Aumann has nicely summarized it in the new Palgrave from 1987, every two-person zero-sum game is determined, so it has precisely one individually rational payoff vector. So one could get the impression that rational players ought to play maximin strategies, and maximin strategies are indeed often called optimal strategies. But in which sense are they optimal? It turns out that providing normative foundations for maximin play is surprisingly difficult. So for instance, if you assume common knowledge of rationality, this characterizes the solution concept of rationalizability, which was introduced by Peirce and Bernheim. And this is equivalent to the iterated elimination of dominated actions. But in the example game here, for instance, none of the actions is strictly dominated. And therefore, every strategy is rationalizable. So clearly, one needs more than just common knowledge of rationality. So we are by no means the first to address this question. So in the interest of time, I can only briefly list some of the previous approaches. There's a much more thorough discussion of related work in the paper. So there's a large branch of research called epistemic game theory, which studies models in which the players do not actually randomize, but that their beliefs are probabilistic. So these kinds of results typically make assumptions such as that rationality is mutually or commonly known, and that the beliefs of the players admit a common prior. Then there are also characterizations of the value of a game. So characterizing the value is actually weaker than characterizing maximin strategies. And this can be easily seen by looking at symmetric zero-sum games. So the value of every symmetric zero-sum game is 0, but still finding maximin strategies in symmetric zero-sum games is non-trivial. So they contain more information. All right, so our approach differs in the listed approaches here in that we characterize maximin strategies via decision-theoretic axioms that require players to behave coherently across hypothetical games. So let me show you the formal model. So we have an infinite universal set of actions, and this is required because we will introduce axioms that establish a relationship between games with different sets and in fact even different numbers of actions. However, all the games that we study will be just regular finite matrix games. So we have a finite set of actions for both of the players in each of the games. So a game is given as a matrix with rational valued entries. So A denotes the set of rows, so the set of actions of the row player. B denotes the set of columns, the set of actions of the column player. So an example matrix could look like this one here. Then we have mixed strategies, delta of A, which are just probability distributions over the rows here. So this is, for instance, a mixed strategy for the row player, which is to randomize uniformly using 1/2 and 1/2 on each of these two rows here. Okay, in case you're wondering why we're having rational payoffs and rational valued strategies, this is because of our proof technique, and I will mention in the end how this can be generalized to real valued payoffs and real valued strategies by making a continuity assumption. Now, a solution concept in our setting is defined as follows. So a solution concept maps a game matrix to a subset of recommended strategies. Okay, one example would be the maximin solution concept, which returns precisely those strategies here. So for the example game here, there's a unique maximin strategy, which is to put 2/3 of probability on the first row and 1/3 on the second row. So what's important to mention is that our model uses independent recommendations. So a solution concept does not return a strategy profile. It only returns a set of recommended strategies for one of the players. So we don't want to have any hidden coordination in the definition of a solution concept. Okay, so now I'm going to introduce the 3 axioms that we need for our characterization. And the first one of these is called consequentialism. And consequentialism is based on the premise that all relevant information is contained in the payoffs. So this axiom only concerned games in which rows or columns are completely identical, so they are so-called clones. And loosely speaking, it means that the set of recommended strategies should be unaffected by those clones. So there are lots of precursors for this kind of axiom, so I'm not going into this in detail. Rather, let me just show you the formal definition and an example. So the formal definition works like this. So we have a matrix game, M. So let's just assume that this is the matrix game M. And this game contains a clone. So there are some rows and some columns that are identical. And that means we can have a reduced form of that game in which there's only one representative for each of these clones. And this reduced form will be called M hat. So there's another game M hat, which only contains one representative of each of these cloned rows and columns. And this is modeled by having 2 functions, 2 surjective functions, alpha and beta here, which maps identical rows to just one row here. Okay, so if there are, for instance, identical rows in the game M here, those could be mapped to the same row in this reduced form game using the function alpha. And there could also be identical columns in this game, which would then also be mapped to the same column by the function beta. Okay. And then the consequence of the axiom looks as follows. So it looks fairly complicated, but actually it's quite simple. So there are mainly 2 important consequences. The first one is that if there are cloned columns, this does not affect at all the set of recommended strategies to the row player. Okay, so and this can be seen by looking that beta doesn't even appear here in the formula. And the second consequence is that if there are cloned rows, then probability can be shifted arbitrarily between those rows because those rows are actually indistinguishable from the view of the player. Okay, so I will show you an example which I think makes things much clearer. Okay, so let's look at these 2 games here. So in the game M, we have 2 columns that are identical. Those 2 columns here are clones of each other. And those 2 rows are also clones of each other. Okay, and then we can get the reduced form game using these functions alpha and beta, which looks like this here. There's only one representative of each of the clones. And then what the axiom says is the following. So let's assume that the solution concept F recommends the mixed strategy 2/3, 1/3 for the game M hat here. And this happens to be the maximin strategy. Then the axiom implies the following. So first, those 2 cloned columns here do not affect the set of optimal strategies. And secondly, and that's more important, the strategies recommended for this game here should put 2/3 on the first row here. And the remaining probability of 1/3 can be shifted arbitrarily or can be distributed arbitrarily between the second row and the third row, because those are just identical clones of this row here. Okay, so the consequence is that the set of optimal strategies is given by all strategies that put 2/3 on the first row here, and the remaining probability can be distributed in an arbitrary way on the second and third row here. Okay, so that's the axiom of consequentialism. Okay, so the second axiom, and that's perhaps the most important axiom in our context, we call consistency. And the idea behind consistency is that a strategy that is recommended for 2 different games should also be recommended if there's uncertainty which of the games will be played. Okay, so you can think of this as having a coin toss which decides which of 2 games is played. And if the solution concept F recommends the same strategies to both of the players in both of these games, then this strategy should also be recommended for any mixture between these 2 games. And this is in fact the only place in our model where expected payoffs enter the picture. So let me show you the formal definition of this axiom. So here we now have two different matrix games, M hat and M bar. And the precondition for the axiom is that at least one strategy is recommended to the role player in both of these games. So the intersection of these recommendations is non-empty. And now we also look at the game from the perspective of the column player. And for this, we take the transpose of the game. Okay, so the negative of the transpose of the game. And that just means, so this term here just means that there's at least one strategy that is recommended to the column player in both of these games. Okay, and if we have such an overlap of recommendations, then the consequence of the axiom is that any strategy that is recommended to the role player in both of these games should also be recommended to the role player in a mixture of these games. And for mixing these games, we just have this parameter lambda, which is between 0 and 1. Okay, so that is just the probability that is used for this coin toss here. Okay, again, let me show you an example. Okay, so here we have two games, M hat and M bar. And now let's just assume that the solution concept F returns the same strategy for the role player for both of these game matrices. And in this example, it's again, is an example, the maximin strategy. So there's a unique maximin strategy here, which is 2/5 on the first row, 2/5 on the second row, and 1/5 on the last row. And the same maximin strategy also works for the second game here. Okay, and the second precondition is that there should also be a strategy that is recommended to the column player in both of these games. And that would be 2/5, 1/5, and 2/5. Okay, so this strategy is a recommended strategy according to the solution concept F for this game here and also for that game here. And now what the axiom says is that for any convex combination of these two game matrices, this red strategy should still be a recommended strategy. Okay, and here we just assume lambda to be 1/2. Then we have this uniform mixture between these two game matrices. Then as a result, we get the following matrix here. And the consequence of the axiom is that the strategy 2/5, 2/5, 1/5 should be a recommended strategy for this resulting game here. Okay, so note that that we only have subset inclusion here. So that means there can be new recommended strategies as well, but all the strategies that are recommended in both of these games here should also be recommended in this convex combination. That's what the axiom says. Okay, so that's consistency. Now to the third and last axiom. This one is called rationality, and it's certainly the least controversial of the axioms that I'm introducing. So it merely requires that strictly dominated actions should not be recommended. And it's obvious that we need some kind of this axiom because so far the trivial solution concept that always returns all strategies satisfies consequentialism and consistency. So we need some axiom that gives some direction. So an axiom that says what's good and what's bad. And we take this axiom here, which is one of the weakest axioms of this kind. So it just says that never best responses should not be played. Clearly, such an axiom has also precursors in decision theory. Let me show you the formal definition now. Okay, here it just says that if we have some game matrix M, and the action A here is strictly dominated by A hat. Okay, so the payoff that you get by playing A is strictly less than the payoff that you get for playing A hat. Then as a consequence, the probability that you put on A should not be 1. Okay, so here you can see that the consequence is quite weak because it just says you should not put all probability on a dominated action. Otherwise, any strategy can be returned. Okay, so the set of strategies returned by F should be a subset of this set here. Again, let me show you an example here. So here we have a 2x2 game, and clearly the second row is strictly dominated by the first row here. And then what the axiom just says is that the solution concept can return any mixed strategy except the one that puts probability 1 on the second row. So that is the only one that is ruled out here. Okay. As you can see, this is, as I said, quite weak, and this is in fact even weaker than the condition that we used in the paper. So we later discovered that we can replace it with this weaker condition. And also in our proof, we only need this condition for 2x2 games. All right, so we now have these three axioms. Let me show you the theorem now. So we have shown that if a solution concept F satisfies consequentialism, consistency, and rationality, then the solution concept has to return maximin strategies. So there's a subset here. So any strategy that is returned by the solution concept has to be a maximin strategy, not necessarily all of them. Okay, so let me give you a quick idea of how this proof works. So if one of the players does not play a maximin strategy, then of course the strategies recommended to both of the players do not constitute a Nash equilibrium. And this is the starting point of the proof, because we take this example and then we use consequentialism and consistency to construct a game in which the player who actually has a profitable deviation, because he's not playing a Nash equilibrium, and we use it to construct a game in which this particular player plays a dominated action with probability 1. Okay, so the main idea is that consequentialism and consistency, when considered in isolation, seem quite harmless, but they become very powerful when used in conjunction with each other. And then, of course, the last step of the proof is that this here constitutes a violation of rationality, because one of the players is playing a dominated action with probability 1. Okay, so the first and the last step of this proof here are straightforward. It's the main meat of the proof is the second step here. So this construction is actually quite intricate, and this is where the interesting stuff is happening in the proof. If you're curious, I suggest to have a look at the paper. We also have an example of how this proof works. Okay, let me just conclude with some remarks about our theorem. So first of all, the axioms that we're using are independent from each other. So for any pair of these two axioms, there's a natural solution concept that satisfies those two axioms but violates the third one. So the axioms do not imply each other. Secondly, the theorem also holds in the domain of symmetric zero-sum games. So for this particular domain, actually the proof can be simplified, which is quite nice. Then we can additionally assume that the solution concept F is upper hemi-continuous, and this allows us to actually make some additional statements. Most of these are not in the paper, not mentioned in the paper. So for instance, this allows us to extend the result to real valued payoffs. We can also have a complete characterization once we assume upper hemi-continuity. So we not only have subset here, but equality. We can weaken consistency by fixing lambda to be 1/2. And we can weaken rationality even further by just restricting it to 2/1 games. Okay, and then it's really perhaps the weakest rationality condition that you can think of. So there are 2 rows and only 1 column. And finally, and this is also an important observation, so once we study the model of general non-zero-sum multiplayer games, we can define solution concepts to return strategy profiles rather than just single strategies. And if we do this, then using almost the same proof, we obtain a characterization of the concept of Nash equilibrium. However, in this model, recommendations are not independent anymore, obviously, because Nash equilibrium requires coordination. And we focused in the paper on zero-sum games because we wanted to have a characterization or justification of maximin strategies when the solution concept returns only strategies. So recommendations are independent. All right, thanks very much for your attention, and I'm looking forward to answering any questions you might have. Thanks.